Take a look at these three molecules. We'll have hydronium, or H3O+, compared to water, H2O, compared to hydroxide, OH-. And we want to rank these from strong to weak acid. We can simply look at the charges and recognize that the more positive is going to be more acidic. So H3O+ is the most positive, making it the most acidic. The more negative is going to be the most basic. And acids and bases are inverse, right? The stronger an acid, the less likely it is to be a base. If an acid donates a proton and base accepts a proton, it's one or the other. OH- is more likely to accept a proton, less likely to donate a proton, making this one least acidic. And H2O being neutral is more negative than H3O+, more positive than OH-, making it the middle. So in order of increasing acidity, OH-, then H2O, then H3O+. Pretty simple example, but here's how you really want to work them out. We'll start by writing out all the acids and then showing their acid dissociation equation, where we take off that H+ and show the conjugate base that forms. So here we have our three molecules. Let's swap out the acidic hydrogen for a red hydrogen so we can clearly see what gets taken away. And then we want to write out the equation. So we'll show a reaction arrow and put -H+ on top of the arrow to imply that we're removing a proton. Or you can put the H+ after the arrow to show that you get a proton plus whatever else follows. I like to do the -H+ because it keeps it neater and lets me compare the conjugate bases without anything distracting. If we remove the acidic hydrogen, we have to keep the electrons there because it's only the proton that comes off. So the electrons collapse back as a lone pair on the atom. And we also have to consider the charge that forms as a result. From H3O+, we removed a positive, so +1 - 1 = 0, water is neutral. H2O is neutral, minus the +1 gives me OH-, and OH- -1 is -1 - 1 or -2. So we have H2O, OH-, and O2- as our three conjugate bases, and now we go back to that rule of happy, stable, unreactive. Now keep in mind, charge, whether positive or negative, is a burden to the atom. Molecules prefer to be neutral in order to be stable. So the more charge you give that atom, the more unhappy it's going to be. Water has no charge. It has a complete octet. It is perfectly happy. The fact that water is perfectly happy means that it is not likely to attack that H+, not likely to reform that H3O+, and because it's more likely to stay, it's more stable as a conjugate base, that tells me the acid that formed it is the strongest acid, because the strongest acid is the one that forms the most stable conjugate base. The next one we're looking at is OH-. OH- has a charge of -1, which is not as good as being neutral, but not as bad as -2, because having a burden of one charge is less than having a burden of two charges, and so we'll call this the middle in terms of its desirability to attack that H+ and reform H2O. And finally, we look at O2-. How did we get that charge of -2? We'll use my formal charge trick of should minus has. If you missed that, go back to the formal charge video on my website, leahforsci.com/orgobasics. Oxygen should have 6 valence electrons. This oxygen here has 8 valence electrons. 6 - 8 is -2. And that's the charge. O2- is not likely to exist by itself, especially in organic chemistry. You do not want to show something like this. It is absolutely terrible, 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 unstable. And so at the earliest opportunity, that O2- is going to attack a hydrogen atom, reform that OH- because OH- is more stable than O2-, and that makes it a very, very strong base. I doubt you're going to see this, but just conceptually, it's a very strong base, not likely to stay, and because it's so likely to reform the acid, it is a very, very weak acid. Now again, this was a simple example where we already knew the answer, but I want you to understand the concept of what we're doing. Yes, we can compare the acids in this case, but by looking at the conjugate bases and comparing, in this case, the charge, you have an easier time understanding what is stable, what is unstable, and the more stable it is, the stronger the acid it came from. The less stable it is, the more likely it's going to reform the acid, the weaker the acid it came from. Now understand this concept clearly, because in the next video I'll focus more on the trend instead of the whole back and forth between strong and weak acids, what's likely to reform and not reform. So be sure to join me in the next video where we look at comparing the atom holding the charge based on its electronegativity or based on its size. You can